In this lecture, we're going to introduce kinetics, which is the study of forces, and specifically focus on one branch of kinetics, and that's called statics. And so when we think about kinetics, we think about forces, and forces are traditionally defined as something that pushes or pulls on an object. A more specific definition of force is that a force can be defined as an action that causes, and very important here, or tends to cause. And this is particularly unique to the study of statics. An object to change its state of rest or uniform motion in a straight line. And so when a force is applied to an object, it doesn't necessarily mean the object is going to move, but the force is going to try to cause movement in such that the object that is in a state of rest will no longer be in a state of rest, and if the object is traveling with uniform motion or at a constant velocity, that velocity will change. And we're going to introduce some tools that we'll need to conduct static analyses. And the first one here that we'll see in the middle of the screen is a vector. And to understand a vector is to understand that a vector will sit on top of a frame of reference. And so we're going to use at this point the standard XY Cartesian coordinate system, where movements to the right that are horizontal would be positive or in the X direction. Vertical directed movements that are upward are positive Y, and counterclockwise rotations will be also indicated as positive. But to come back to our vector, a vector by definition is simply a directed line segment, and we have to imagine a vector that sits on this imaginary yet infinite line of action, and that's what we see here in the dotted line, so that this vector can slide along this line. The components of a vector include the tail of the vector, and this is the initial point where the vector starts, and this is also referred to as the point of application. So when we use a vector to represent a force, that force will be applied at an object at which the force generating element is attached to the object, and the vector is going to be pulling away from the object if it's a pull. The arrowhead is referred to as the sense of the vector, and that's the terminal point. When we take a look at the distance between the tail and the tip of the arrowhead, the entire length of that vector will represent the magnitude. And so if we use the vector to represent a force, then the length of the vector would represent the magnitude of that force. The direction of the vector has two aspects to it. The first one, as illustrated here in the middle of the slide, is the vector sense, and that's indicated by the placement of the arrowhead. So the vector sense here would indicate that the vector is directed to the right. If we took the arrowhead and put it on the other side, then we would say the vector is directed towards the left. The second aspect to direction is what's called vector orientation. And to understand vector orientation, we analyze the vector on the backdrop of a coordinate system, and that's why it's always important to have a coordinate system somewhere in the vicinity of the vector to give that vector the proper orientation. Now, vectors can be put together into one larger vector called a resultant vector. That process is called vector composition, and we'll illustrate that with this anatomical example. Vector composition, as the term suggests, is a process where we take two or more vectors and we use one resultant vector to represent the additive effect of two or more vectors. And so what we see here is an illustration of the anterior thigh muscles, or the quadriceps femoris muscles. And it seems a bit subtle, but it's very important that in the upper right hand corner I have drawn a coordinate system that will be used to interpret all of the vectors of this particular scenario. So what I'm going to do here is I'm going to use a vector. I'm going to center this vector at the midpoint of the patella, where the attachments for the superficial quadriceps femoris muscles converge. And I'm going to draw a vector to represent the force generated by the distal component of the vastus medialis muscle. So what we're seeing here is the manner in which we label vectors. So I'm labeling this vector with a capital letter F with the small arrow on top to indicate that this is a vector quantity. And in subscript, I'm going to give this particular force vector a unique label here. And this one is for the distal portion of the vastus medialis muscle. Now, there's a proximal portion of the muscle, of the same muscle, the vastus medialis, and if I use a vector to represent the force generated by the proximal portion, then I would label that appropriately VM for vastus medialis proximal. We know that we have two centrally located muscles. One is deeper to the other. The more superficial muscle is the rectus femoris, and the muscle directly underneath or deep to the rectus femoris is the vastus intermedius. And when these muscles contract, they generate a force and pull on the patella. The largest component of the quadriceps femoris muscle is the vastus lateralis. And because these muscles are located in different positions but all converge through the patella, they will all have the same point of application, but the directions of these vectors, as well as the magnitudes which reflect the strength of the muscle, will be different. Vector composition is a process where we can take these four vectors, add them up, and we will get one resultant vector, and we designate that as the force of the quadriceps femoris muscle group. And so what we see here is a long vector, greater in magnitude than any of the individual components, and reflects a direction that's just slightly lateral to that of the RF and the VI. Now, if we can combine vectors, we can take one vector and break it up into component vectors, and that process is called vector resolution. So what we're doing here is we're decomposing one vector into two constituent vectors, but we do that based on a frame of reference. And once again here, we always have to draw our frame of reference in order to interpret what we're doing with our analysis. So in this particular example here, we see a diagram indicating a seated single leg knee extension task. And now this is potentially complicated, because although I initially put the standard XY coordinate system in the bottom right hand corner, we have the segment we want to analyze, which is the lower leg and foot, that's not aligned with either X or Y. So what we do here is we create another coordinate system by taking our XY. In this case, I rotated the XY clockwise to align the X-axis with the line of the segment that we wish to analyze. But we can no longer call it XY. X is always going to be perfectly horizontal. Y will always be perfectly vertical. So what I'm going to label this is what's called X prime, and Y becomes Y prime. And this is the coordinate system that is specific to the analysis we'd like to do. Now, to hold the leg in a knee extended position, foot is off the ground, we know that the quadriceps femoris muscle, or the thigh muscle, will produce a force. That force travels through the quadriceps tendon, through the patellar tendon, and is applied at the tibial tuberosity. And we can use a force vector to illustrate the force generated through the patellar tendon at the tibia that will cause a knee extension, and we draw that vector through the actual soft tissue of the tendon. And we would give that an appropriate label called force of the patellar tendon as a subscript. Now, because we have our coordinate system here specific to the position of the leg, we can take this resultant vector and decompose it into two separate parts. We have a vector that is directed perfectly perpendicular to the x-axis, or the x-prime axis, or the to the lower leg, and we're just going to label that force of the patellar tendon in the y-prime direction, because this vector is parallel with y-prime. We call this the rotational component, because when this force vector, when this part of FPT is attempting to drag the tibia into the direction of that vector, of course the tibia doesn't move in a linear manner, it actually rotates because of the construction of the leg. But it's this smaller component of FPT that will cause the rotation. We see the other component here of FPT, the much longer component, which means that it's a larger component. We're going to call that FPT X prime. X prime because it's parallel to the X prime axis. So this component of FPT will attempt to drag the tibia in the direction of this vector, and it's going to hit the femur. And that will create a reaction force that we'll address a little bit later. And we call this the stabilizing component, pertinent to any human joint when a muscle is attempting to produce a force across that joint. The other important principle that we need to understand when generating a kinetic, or more specifically a static analysis, is one of Newton's laws of motion, and that's Newton's second law, often referred to as the law of acceleration or referred to as the law of momentum. And this law states that the rate of change, and this rate of change is a time rate of change, of momentum is proportional to the applied net external force in the direction of the force. So this begs the question, what is momentum? Well, momentum is just simply defined as the quantity of motion an object possesses. And mathematically, momentum is when we take the mass of an object and multiply it by the velocity, or how fast that object is moving. Now, if an object is not moving, if it is at rest, therefore its velocity is zero, therefore it will have zero momentum, but that doesn't mean that forces cannot act on that object, as we'll determine in this unit. The equation illustrating Newton's second law is that the sum of all the forces, and this can be up to n forces acting on any object, is going to equal to the mass of that object times the acceleration of that object. And what that tells us is that when forces are applied to an object, those forces will tend to want to cause that object to accelerate. Another important element to understanding kinetics is that forces will often induce rotations. And the counterpart to the Newton's second law here for forces is what's called a moment of force. And that's going to be equal to I alpha. I refers to what's called the moment of inertia, where alpha is angular acceleration. But this is something that we'll get into in a little bit more detail in the next subsequent lectures. And so what we're doing here, the Greek letter uppercase sigma indicates that we're going to add up all the external forces as well as the moments of force acting on an object, and the net sum of all those forces will tend to cause that object with mass to accelerate or to rotate at a particular acceleration. Now, if we have, in this case here, if acceleration goes to zero, in other words, if an object is at rest, this equation changes to the sum of the forces equals to zero. Now this could be potentially misleading, but this doesn't mean that no forces are acting on an object. What this says is that the net effect of all the forces will be zero, so the object will remain in a state of rest. And this is what we call a static condition. And so a static condition is defined by a system that is at rest, so it's not moving, or a system is experiencing zero acceleration where it has constant velocity. But in our applications, in applying static conditions, we'll always use conditions in a state of rest. Likewise, if we're dealing with a rotating system, and if that rotating system has an angular acceleration that goes to zero, then this equation changes to the sum of all the moments of force will equal to zero. It doesn't mean that there are no moments of force acting on the object. There certainly are, but their net effect will not cause an angular acceleration. And so when we talk about conducting a static analysis, the objective is to gain an estimate of the forces imposed on a system, and we're going to use what's called a free body diagram to start the process of conducting a static analysis. And the reason that we want to gain an estimate of the forces that are imposed on a system is that some of these forces could be potentially damaging to the structure of a given system. And in this example, here we see a person holding their lower leg in a knee extended position, and this leg has attached to it a rubber elastic band to provide additional resistance to the knee extensor muscle group. Now when we look at this picture, very complicated, very asymmetrical system to analyze. So what we do is recreate what's called a model of the system. So here I'm just drawing a simple stick figure. I'm using a triangle to represent the foot. Now we have a very simplified diagram, and that's the goal of a kinetic analysis, particularly a static analysis, is that the system is often too complicated to analyze directly, so we simplify it as much as we can to the point where it still possesses a representative set of characteristics to the original system. And that's what a model is. Now the model is what we will analyze, and we'll do that here in the next part in our next video.